right. Okay. So in this talk, I'm going to present the wide-field spectroscopic telescope project as a potential next large ISO facility after the ELT. So as you will see, this project is reach a similar goal that MSc, but with a number of important differences. So that's I'm going to show that. So let me see, change. Okay. So yeah, so that's it seems maybe a bit premature to discuss what would be next after the ELT. So the ELT is not yet there. It's progressing relatively well, but it's a very big project. And but as you can see from the dates, we started to think about this project already in 1988, which at that time was called ALL. And then it was really decided to focus on this project at the Marseille conference in 2006. So, and the planned first light is still planned for 27. So this project takes something like 20 or even 30 years to be done. So I think even if it's not yet there, it's really important now to start to think what would be the next. And we guess that WST could be a strong candidate for European astronomy and other partners. So, what would be the landscape in the next 10, 20 years? So, because it will be a very interesting landscape, because there will be a large number of new facilities. So we'll have, of course, upcoming ground-based telescope like LSST, SKA, which has been discussed here at Lens, CTA, and possibly other, but also upcoming space telescope. James Webb is there today, but soon we'll have Euclid, Raman, Athena. And of course, all these facilities have a very big imaging capability, and they will detect and classify a huge number of objects. But however, I think image, whatever their quality, are not enough. Spectroscopic information is absolutely needed to understand what these objects are. Now, if we just take the example of LSST, the number of sources expected after the 10 years nominal survey is almost frightening. So 20 billion of galaxies, 70 billion of stars, down to a magnitude of 27. Then only a dedicated spectroscopic facility will be able to fully realize the scientific potential of these wide field imaging surveys. Of course, we didn't wait until today to work on this very important challenge. We are building a multi-object facility on the 4-meter class telescope. A good example is Foremost for the Vista. Is a telescope, but there is others on the 4-meter. There are also new MOS instruments to be installed on the current 10-meter class telescope, such as Moons for the VLT or PFS for Subaru. So all these facilities will produce a great science, but they cannot really meet the formidable challenge to follow up the deluge of new sources expected for the upcoming image capability. Well, the reason is that the 4-meter facilities are limited to the brightest source because of the aperture of the telescope, and that the new MOS, which are installed on the 10-meter, have limited multiplex capability. In addition, they have to share their telescope access with other instruments. Of course, in this game, we will have the ELT soon, but the ELT will have a very limited impact because of ELT, by construction, have their intrinsically small field of view and therefore limited multiplex capability. So then I think this conclusion, which was raised by the community, that a new spectroscopic survey facility on a dedicated wide field 10-meter class telescope equipped with a very high multiplex MOS is absolutely required if we if we want to progress on this area. So MOS is a very powerful technique to perform spectroscopic survey, but it's not anymore the only one. More recently, the second generation of panoramic integral field spectrograph with their larger field of view and exquisite sensitivity have opened a new way to perform deep spectroscopic survey. MUSE is the best and today almost unique example of such instrument. Such instrument can address a large variety of science cases, so it's not surprising that MUSE is the most demanded with an oversubscription of 10 and the most productive instrument of the VLT. However, the field of view of MUSE, also much larger than all other existing integral field spectrograph, is only 1 square arc-minute. That's relatively small. And so a larger field of view is highly desirable. But MUSE with its currently with its 50 cubic meters and 7 tons already fill up the full Nasmyth platform on the VLT. You may wonder how competitive an integral field spectrograph with a sort of miserable 1 square arc-minute field of view can be compared to a MOS. For example, VMOS with its 220 square arc-minute field of view and its multiplex of 1000. So because that's something maybe more new, I want to give an example. So the candle's good south, as you know, is the most extragalactic emblematic field observed by Chandra and Hubble in the 2000s. It has the greatest collection of high quality, very deep, multi-wavelength data. 20 years of observation with the MOS on the 10-meter class telescope, plus some additional observation with the HST GRISM, have been able to produce a collection of 3,000 of galaxies. So you can see the distribution of redshift and magnitude of this galaxy. Most galaxies have magnitude of 25, and the number of high redshift galaxies is relatively small. So much smaller than what has been observed in the field in terms of the spectrophotometric redshift. So now comes MUSE. So in a fraction of the telescope time, focusing on the small 3 by 3 arc-minute ultra-deep field, MUSE has been able to get a similar number of galaxies than all MOS observations obtained in 20 years' time. But as you can see, with a very different magnitude and redshift distribution, MUSE can detect extremely faint galaxies. In fact, a large fraction have magnitude larger than 30, below the HST detection limits. And also you can see that the number of high redshift galaxies is also another magnitude larger than in the MOS sample. So this is very illustrative of the high complementarity between MOS, multi-object, and the integral field spectrograph observation. With the MOS, we probe the bright end of the luminosity function, while we access the faint end with the integral field spectrograph. And it's the same with redshift. MOS will give access to the low and medium redshift population mostly, while the FS probe the high redshift regime. So this is very complementary, and even more because both have some sort of selection effect, of course, because with the MOS you select in galaxy with imaging, large band photometry. So you will mostly probe a galaxy with an important continuum, and with the FS, you will probe a star-forming galaxy. So this is also complementary. So, but of course, in addition to the MOS, to study the galaxy population, and AFS have another benefits. First, as we have seen, can study sources that are not visible in the broadband imaging. Second, it can measure extended ionized gas emission at different scale, around the galaxy in groups, for example, or in the circumgalactic medium at a scale of a few hundred of kiloparsec. and even up to the intergalactic medium at scale of megaparsec. So that's also a very important matter. So to understand, because you can not only get the galaxy themselves, of course, but you can get the surrounding and the interaction between what happened in the CGM and the galaxy, which we know is a critical measurement for understanding galaxy evolution. So last, but I would say not least, because an interface spectrograph gets spectra of all spark cells within its field of view, it has, of course, a great potential of serendipitous discovery. So it's then obvious that a larger field of view interface spectrograph on a dedicated 10-meter class telescope will have a huge scientific impact. So the WST proposal is really the idea to join the two complementary approach by building a 10-meter wide-field telescope, in fact, a facility, with a MOS, with a massive multiplex capability, and a giant panoramic interface spectrograph, both working in synergy. So what are the customers for such a facility? So if we look to the results of a poll initiated by ESO, for example, that show that 75% of the astronomical ESO community request such a facility for their science. We can also look, it's interesting, to the ESO publication papers. So from the 700 papers published in 2021, for example, you can see that a quarter of them are produced by MUSE. Another quarter is produced by the MOS instrument, like VMOS, FORCE, and GIRAFFE. And then if we had the high spectral resolution spectrograph like X-Shooter and UVS, so it's almost 80% of all publications that are currently done at ESO. So a facility that will encapsulate this sort of facility, but much upgraded in a way, would have been really important for our science community. And then it's not a surprise that the ASTRONET, in its last report, recommended the wide-field spectroscopy facility as one of the 3 new large facilities for the next decade, together with CTA and EST. So, from all the previous consideration, we have defined a preliminary set of ambitious top-level requirements. So among them, there is a field of view of 5 square degrees. So just to realize, I show in this plot to show how big this is with respect to the VLT. So you can see the different scale. The MOS multiplex is also 1 order of magnitude larger than the current generation, as it should be. A high resolution mode is foreseen for galactic studies, and the interface spectroscopic field of view is 9 times bigger than MUSE, and its spectral range covers the full optical domain in one go. So it's more or less the combination of MUSE plus blue MUSE multiplied by 9. And one very important aspect here is we want to operate simultaneously the FS that will sit in the center of this big field and the MOS, ready to make the science. So with such top-level requirements, WST stands out of all other existing or planned facilities. This is shown in these 2 plots. On the left, you see the MOS facilities, which are currently existing or the ones that are planned in the coming years or decades. So on this plot, you show the multiplex versus the telescope aperture size are shown for these facilities. The area of the circle is proportional to the étendue, which in a way is related to the speed you can perform a survey. So that's for the left plots. On the right plot, you can see the existing few panoramic interface spectrograph. You can see that their field of view versus telescope aperture. And as for the MOS, the circle size indicates the étendue. As you can see, the combination of two, WST will outperform all other existing or planned facility. So, in order to meet such ambitious requirements, we will design WST as a facility that we will not design a telescope and then put instruments on the telescope, but they will be designed together. So just looking to the expected number of spectrograph and detector, it show why this is needed. So more or less 200 spectrograph, 500 detectors. These are impressive numbers. But on the other hand, it's not so different from what we have built. LSST have 200 CCDs, MUSE have 24 spectrograph, and HETDEX 79. So it's larger, but it's not such larger. WST will be built in the southern hemisphere as a perfect match to LSST, TA, SK as well. And as an ESO facility, we are looking to the available peaks in the Paranal Amazonas area and also in the La Silla places. So there are already a number of potential target sites that we are starting to evaluate. So this talk is too short to describe all the transformative science that will result from the WST, but I will just briefly give three examples. So the first one is the mapping of the large-scale structure of the universe. So the left plot illustrates how the high multiplex capability of the MOS will enable to reconstruct the large-scale filamentary structure. On the right, here you see that the EFS simultaneously will map the distribution of galaxies at smaller scale and higher density, but also it will be able to directly trace the filament in emission. So that will give you a very interesting view of the distribution of galaxy. The second example in cosmology is shown in this slide. The figure on the left displays the equation of state of dark energy for a different model. As you can see, the difference between the model is maximum at high redshift. And this is really a domain where WST will have a large impact because of its large aperture and massive multiplex capability. It will be able to perform measurement needed to reach the precision. So on the right, you see the relative error on the Hubble constant as function of the redshift compared to other facilities. So with almost 1 order of magnitude gain in precision because of the large number and compared to other facility and the access to high redshift, WST will have a great impact on the measurement of the dark energy equation of state. In this last example, we focus on the high spectral resolution capability of WST. Thanks again to its greater aperture and massive multiplex, WST will probe main sequence stars, which are the yellow curves, to a much larger distance than the current facility, for example, foremost. And for the red clump stars, WST shall be able to probe them over the entire galaxy accessible from the south. So to quantify, we estimate that WST will provide in just the first 5 years of operation with the most medium resolution, 250 million galaxies down to a magnitude of 24.5 over the entire accessible sky and 25 million of stars over the entire galaxy and local group. With the most high resolution, 2 million of stars, but with a much higher spectral resolution, down to a 17 magnitude and over most of the galaxy. And for the IFS, WST will deliver 4 billion of spectra located in 7,000 fields over diverse environments from low density to galactic dense fields. So of course, there are some challenges associated with the data, like all this big facility. The first is the volume. Of course, it's a big volume, but it's not so difficult to probably to handle in the next decade. The second is the data complexity. While imaging capability like LSST will produce images, the WST will produce data of different kind and different dimension from 1D to 3D. Another challenge is the potential carbon impact. Of course, we need to take care very seriously on that. And the plan is to keep the raw and reduced data close to the telescope in a data center powered by a solar plant. We also plan to take care of the carbon impact in the design of the facility itself to minimize it. So to perform this concept study, we have assembled a large consortium of 23 institutes currently, in addition to ESO, and they represent a large fraction of the ESO member states. We have also all major institutes from Australia, and you will understand the next line why. And all together, I think we channel quite a large experience, because we have designed and built 9 telescopes, 8 multi-object spectrographs, and 10 integral field spectrographs. So we plan to work on this study for the next 5 years, moving from concept to preliminary study. So the study will end in 2027 at the same time of the ELT first light, hopefully. But it's also at the end of the Australia-ESO agreement. And as you may know, Australia is wanted to become a full member of the ESO. And for this accession, they would be certainly interested to provide additional funding to build such a facility as part of their in-kind contribution. So we assume that at the end of 2027, that would be an appropriate time to transfer the leadership of this project, which currently is within the community, to ESO and as the next ESO project. So where are we? So we've just started the concept study. We're working with the pre-design of the facility. We are making progress. We'll make trade-off, update the cost estimate. Currently expected $500 million. And in parallel to this, we want to raise the community awareness. And this is what I'm doing now by giving such talks. But also we are organizing a science case workshop, and we'll be writing a white paper.
Long live India and France friendship.